What up, everybody? Welcome to Coffee Hour with Paul. Here we are on a Monday morning. Thanks for everybody joining me today. I do want to give a shout out to my big brother, Chip. Happy birthday. And it's great to be back in Virginia. We just got our first snow of the year. It's about 5 or 6 inches. I don't like snow. I've been in Texas for the last 11 years, and we had one little snow event out there. And then, of course, we have the old, well-publicized breakdown of the windmills because nobody put antifreeze in them, I guess, or whatnot. But anyway, thanks for joining me today on Coffee Hour. We're going to try to cover 2 topics today. But, of course, if you have questions, please feel free to put them in the comments. And as always, let me know where you're from. And if you're in our program, let us know if you're in our program. We'd love to see it. And that type of thing. So, Dan, welcome. Good morning. Welcome to the Coffee Hour. So we do this for those that are new that haven't come here before. We do this every morning, Monday through Friday at 8 a.m. just to get your day started, answer any questions you may have before you get out into the field. It can be on any topic. It can be on business. It can be on, you got to fire somebody today. You want any advice? I've had to do it. But it also is for just about any topic that you want to talk about. We can discuss it. In the process, we'll try to give a little lesson and let it get something out of the coffee hour. Today, we're going to start off with the 10-foot secondary conductors, quickly move through sizing of that. If you're not familiar with the overcurrent protection rules and all that stuff, we did an extensive coffee hour on that a couple ago. So make sure you go check that out. All of our coffee hours are available on our YouTube channel, as well as they will be on their own separate channel over on Fast Track's Tube here. Usually, with probably within the next day, that channel is going to be set up, so you can go watch all of the previous episodes of Coffee Hour. Let's do some shout outs. Dan is in Chicago. Again, y'all already have snow probably, so this is nothing new to you. It is for me. I don't like snow. Okay, let's see. Edgar, good morning out in California. Glad you could join us. Paul in Houston. Thanks for joining, Paul. Glad to have you here. All right. So, again, let me know where you're from. If you're in our program, let us know. So today's episode, we're going to be talking first about the transformer secondary conductor rules. And if you haven't watched the previous show, you'll know that they are not taps. They are secondary conductors. There's a defined term to explain what a tap actually is. And basically, a tap is a smaller conductor connecting to a larger conductor, be it at a lug or an actual conductor, where the tap conductor is not protected at its ampacity at the point where the tap takes place. Okay? So when you hear that phrase from people say you can't tap a tap, basically means simple terms, if I have a conductor and I tap it, I can't tap that tap in order to get another one because, again, that conductor that's tapping onto the feeder is not protected at its ampacity, but it's using specific allowances in the code to still be considered protected, whereas that one that's tapping onto the tap is not. Okay, so again, we're not going to be talking taps because we have talked taps before, and that is in a previous episode. We want to get straight into the secondary conductors. And on this one, we're going to jump right into the 10-foot secondary and solve that. And we're going to use the example out of Link because it's a nice, clean example. And then we're going to look at the 25-foot feeder tap. In the last episode, we did 10-foot feeder taps, and we talked about taps. Now we're going to move into the secondary conductors on a transformer. We're going to be talking about those secondary conductors, and then we'll jump back if we have time and catch that 25-foot feeder rule. So you see how I'm going to be jumping in episodes back and forth. That's to make sure that people follow the episodes. And I don't just do one on secondaries and then one on just on feeders. It's not how we're going to do coffee hour. Okay. All right. So let me get over here. So this is the National Electrical Code. And this is the Link edition, by the way. And it's also 2023. So people have asked, do you do 2017? We have courses on those, but I'm always using the latest edition of Link or of the NEC. So that's the one I like to use to illustrate different code things. So, all right. So here's the first. So we're talking about transformer secondary conductors not over 10 feet. Okay, so the concept of this is, if I had to illustrate that, paint a mental picture for that, then I would say, okay, so you folks are familiar with, you got your panel, you have a breaker, you're coming out, you're feeding a transformer, okay? Dry type transformer, right? Out of that transformer, we're going to be coming out of what's called secondary conductors. They go straight to the lugs on the secondary, and they come out, and they'll go over to typically hit a panel enclosure, and it'll terminate into typically a main breaker, right? And so those conductors are considered secondary conductors. They are not taps. Now, granted, they connect into some lugs inside of the transformer, but that does not make them a tap conductor, because by definition, they can't be, right? But many people will say that. You'll hear people say they're taps and things like that. And again, whatever helps you get through the day. It's kind of like using the term sub panel. Sub panel is not a term that's typically used for our remote distribution or a feeder panel or a feeder load center. However you however you want to call it, people will use the term sub panel because it's just easy for them to identify with what we're talking about, that type of thing. Argo, thank you for joining me down in Atlanta. Glad to have you here. What do we got? Mr. Marava, is that it? Mr. Marava, what's up? Lewis, oh, that's better. Lewis from North Carolina. Thank you, Lewis. Thanks for joining us this morning. All right, let's get on over and look at this thing real quick and knock this out of the way. All right, so these secondary conductors. It says, if the length of the secondary conductor does not exceed 10 feet and complies with all of the following. So this is not a partial rule here. You got to comply with everything in order to do this tap rule. All right. And so this tap rule, I catch myself doing it too. This secondary, see how easy that happens? This secondary conductor rule is basically saying, similar to the tap, saying, okay, you're connecting to a transformer secondary, and there's a possibility that it could be smaller than what the transformer's output is. Of course, it could be equal to the output. And of course, it could be larger than the output. You can have a larger conductors than you need if you want. It's just you got to be careful if it can fit in the lugs, that type of thing. But what we do know in this case is, from that transformer, I can go up to 10 feet, okay, and determine the size of those conductors based on this allowance here. So 240.21c, and I'll show you. This is 240.21. Let's go back here. Here we go, 240.21, and we're dealing with C, transformer secondary conductors. And in our case, we're dealing with C2. Again, we're in the 2023 edition. So what do we got? David, Culpeper, Virginia. Snowy morning? Absolutely. Right down the road from me. It is snowy here. We got about 5 inches. I don't know what you got. But TJI, good morning, sir. Thank you for joining me from Alabama. There you go. South Alabama. You're not getting any snow. You might have got some storms the last couple of days, but you're not getting any snow. I wouldn't think you would be down in Alabama. All right, so let's talk about it. So the first thing we're going to talk about, those secondary conductors. Again, remember, in your mind, picture transformer, load side of transformer, output of transformer, whatever you want to call it, going out of the transformer and going into an enclosure, let's say, with a breaker, okay? So it says, the ampacity of the secondary conductor is as follows, okay? Not less than the combined calculated load on the circuit supplied by the secondary conductors. So, okay, first, so from our design's perspective, we have to know what the loads are. And we could have a transformer that's feeding 2 separate panels that each would be, let's say, 100 amps, okay? And then you'd have the combined, whatever, in each one of those panels, whatever's being supplied by that panel is going to be, the actual conductor can't be less than that. Okay, so this is minimum rules, not less than. You would treat each separate, but you also want to make sure that transformer can handle those multiple loads. I don't know how many of you have actually seen where transformer is actually coming out of it is feeding multiple loads, but you can. There's nothing that says you can't do that. But one thing's for sure, if we're coming out of the transformer, we're hitting that panel with that breaker, that we want to make sure that the conductors at least can handle what? The combined load that's going to be in it. So you're going to have to do a load calc. You're going to have to know what you're putting in that freaking panel. Okay? All right? So that's that. And we all know that you all know how to do load calcs. Let me check. Okay, no, we're good. So we know that's not a problem. Next, B, it says the ampacity of the secondary conductor is not less than the rating of the equipment containing an overcurrent device supplied by the secondary conductors. Okay, so you could have a piece of equipment with multiple breakers in it. You could have a separate piece of equipment that's being supplied by a transformer. It doesn't have to be just a panel board. Okay, but one thing you got to remember is that if it's the equipment's rating, that equipment has to contain overcurrent devices. Okay. Now it says, or not less than the rating of the overcurrent protected device at the termination of those secondary conductors. Okay, so this has to do with when it comes out of the panel, out of the transformer, hits this panel. If it's a panel enclosure, okay, a remote distribution panel-ish style, okay, but it's feeding that panel with a breaker, and it's terminating in a breaker, then those conductors cannot be less than the rating of that device. So this is where you see people say, well, if those conductors are terminating in a 200 amp overcurrent device in that panel that's right next to the transformer, if it's terminating in a 200 amp device, then those conductors cannot be less than the rating of whatever the overcurrent device is that it terminates. So they would have to be rated for 200 amps. Makes sense? If it was a 300 amp, it's got to be rated for 300 amps. Makes sense? Okay, so not less than the rating. That's probably what we're going to see the most, right, in our applications, is that we come out of this panel, and we're doing it because we need different voltage. So maybe we have 480 volt in the building, and we need a 12208. So we're coming out of that, hitting a transformer pretty close, okay, under this 10-foot rule. We're coming out, hitting a transformer, and then on the load side of it, we're coming out and hitting a panel, so we're changing the voltage for our whatever. Maybe we're doing lighting or something like that, where maybe the 480 was generally for motor applications, and we need to have a transformer in order to get for lighting loads, things like that. Okay, so that's what you might run into. But those secondary conductors, if they terminate into a 200 amp device, then they have to be rated for 200 amps. Now, the next biggest thing in this is we get that, right? Is the question they go is, well, let's say for craps and giggles, it is being terminated into a 400 amp overcurrent protected device in a panel. Okay, let's just say it is. Transformer's sized properly, everything's done, loads have been calced, and those secondary conductors are going to terminate into a 400 amp overcurrent device. Now, one of the things to remember is that those conductors, remember what it says, since it's terminating into a 400 amp overcurrent device, that means those conductors have to be rated for 400 amps. Well, some engineers, not all, some will design it and say, well, transformers load limiting, yada, yada, yada. I want you to use a 500 kc mil. Okay, well, a 500 kc mil has an ampacity of what? And we always assume copper unless stated otherwise, right? So we'll go look at a 500 kc mil. We're at this table, so we're right here. Here's a 500 right here, and it looks like it's good for 380 amps. Again, people ask, I can't use this 90 unless I'm doing adjustments and corrections, or everything is rated 90. And chances are the lugs probably in a transformer may or may not be rated 90, but the ones that are at the breaker in the panel board probably not going to be rated 90. Okay, so we're going to be in the 75. So it's 380 amps. Now, the question that people ask, right, is they go, well, if it's 380 amps, can I use the next size up rule and terminate that on a 400 amp overcurrent device? And the answer to that is no, you cannot. And people say, well, where does it say that I cannot do that? Right? Well, we have to go back to 240.21. And if we come back to 240.21 and we come down here to C, because we're doing secondary conductors, right? It says right here, it says section 240.4b shall not be permitted for transformer secondary conductors, okay? So that is the rule, okay? So that's what we're into when it comes to that. We're like, okay, so since those conductors were 380 amperes, can I terminate them on a 400 amp overcurrent device? Not under the tap rules, and certainly not under the secondary rules. I can't. So I'd have to increase the size of my conductor. So in this case, in order to make sure it's at least the rating of the overcurrent device, then I would increase this from a 500 kc mil up to a 600 kc mil, which is going to have adequate ampacity to be equal to or greater than the rating of the overcurrent protected device. Okay, that type of scenario. All right, so that's an important part to realize on those tap rules. Now, we're going to have other episodes where we talk about where it can be the secondary conductors can be, let's say for industrial installation, the secondary not over 25 foot, so you can go 25 foot. We have outside secondary conductor rules, which are unlimited because they're outside. So we don't have a length limitation on them, not inside. And then, of course, you'll have other types of applications that we'll be talking about. Secondary conductors not over 25 feet, which will be the next episode when we talk about the 25-foot secondary conductor rules, that type of thing. Okay? So let's see here. We got a question. And Dan asks, if the conductor is rated for 400 amps, does it matter how far the overcurrent protector is from the transformer? Yeah, so if you're utilizing the 10-foot rule, okay, then yes, it matters. You know why it matters? Because there's no overcurrent protection at the connection to the transformer. So this is a limiting length rule because there's no protection there. And so you're utilizing this secondary conductor rule because there is no protection at the point where it makes a connection to the transformer. Now, if you want to put a 400 amp right there on the transformer or at the transformer, then after that, it doesn't matter how far you go because those conductors are protected. But the whole premise of the rule here is you're applying the 10-foot rule. So if you got a transformer, it's got no protection on it, right? And you're required to have that protection. Let's say you're using primary, secondary protection in 450.3, okay? Then if that's the case, then you have to protect that transformer secondary. Well, if you have to have primary and secondary protection, and you also are using that allowance for protecting the transformer, now we have to protect these conductors. And the whole point of the secondary conductor rule, see how easy it is to do that? The whole point of the secondary conductor rule is to limit it. If you could come off of that transformer with the 400 amp rating and run it unlimited, then what would be the purpose? What would be the point of these secondary conductor protection rules? Because you're not protecting those conductors. And the whole point is it's similar. That's why it's in 240.21. It's very similar to the tap rules. So you still have your limitations. Now, if you want to, again, come out, what people do is they'll come out of that transformer, hit a single breaker in order to be able to protect it, let's say at that 400, and then they can run it from there any length they want. Again, taking voltage drop, which is not a requirement, but taking those things into consideration. But once you meet those rules, because now you have the transformer protection as well as you are now following the secondary conductor rules for those 10-foot span. Make sense? And so we will go over the 25-foot one and all those other type of things. But what you're going to do is if you need to go longer, you just hit the disconnect within your 10-foot, meet your secondary rules, and then you can go from that 400 amp that's right there, and you can hit a panel and then go as long as you want. Again, within reason, of course. Good morning, Frank. Thanks for joining me. What do we got? We got Manny. Manny, thank you, Manny. Always there. Anthony. Good morning, Anthony. Mr. Inspector. Let's see here. Russ and Peggy. I bet Peggy's still in the bed. Good morning from Arizona, up early out in Arizona. Good morning, Pittsburgh. I'm sure y'all are probably getting snow. Y'all will get snow from this thing, probably a lot more ice than snow. All right, Dan, I'm glad. I hope that makes sense. But don't worry. We're going to talk about 10-foot rules outside. That's what coffee hour is all about. We're not going to try to cram everything into one episode. These are just for us to get our days moving and get rolling. All right. All right, so let's get back to our lesson here. So we're back here at the 10 foot. So we made sure our ampacity is fine. Now, we do have an exception. The exception says where listed equipment such as surge protected devices is provided with specific instructions on minimum conductor sizing, the ampacity of the tap conductor supplying that equipment shall be permitted to be determined based on the manufacturer instructions. So this is where you may have some special equipment, okay? And even they say the word tap in here, right? They have some special equipment which may come with the manufacturer's requirements, and manufacturers are more restrictive than, let's say, the National Electrical Code. Typically, the manufacturers, we hope most of the time, the manufacturers will be equal to the NEC, but there are some occasions where they are more restrictive. And if they're more restrictive, you follow the manufacturer. If the manufacturer is less restrictive than the NEC, then you contact the manufacturer and then work with your AHJ, because, again, we don't know if that equipment maybe was made overseas. We don't know if what kind of testing. We will hope that it's tested by NERDL, nationally recognized testing laboratory, where applicable. So again, you have to work together, but we want, as an electrician, we have to be careful. But there are certain things, like surge protected devices, that we know that those conductors are not going to be the same size as what they tap onto or connect onto, right? So there are special allowances for that from a manufacturer, that type of thing. So that's all that exception is saying, okay? Good morning, Alex. Thanks for joining me. And Anthony says, no snow down, I believe, in balmy Florida. Is that where you're at? And there's snow down there? If it's snowing in Florida, I know you have gotten it before, but that would be more of a rarity, wouldn't it? Okay. Dan says, so after the overcurrent protecting device, it becomes a feeder. For all intents and purposes, yes. It's on the load side of an overcurrent protected device. So, but it also... after it comes off of that, it could, if it terminates from there into a piece of equipment, it could also be a branch circuit as well. Okay, so that type of thing. So as you'll see, the secondary conductors that prohibit that application, all right, are very specific here. Remember, 240.21C1, it says you can't use the 240.4B. It's specific to what? This rule, secondaries. Once it leaves that and hit on the load side of an overcurrent, you've already met this rule when you hit within the 10 feet. After that, the regular rules within the code come into play. All right. Let's see here. Miles says, thank you for your hard work. You're most welcome. You have a master exam in 2 weeks, and your morning sessions along with your Fast Tracks program been a huge help. Well, that's awesome. Thank you for joining us, and diligent. You'll get it. Stay focused and stay dedicated to it. You'll get it. I guess, folks, I tell people all the time, I've been doing this for coming up on 39 years in another month or so, and I am just as excited about the electrical trade today as I was that many years ago. Technology is changing. New things like Class 4 fault managed systems are coming in to learn. I mean, most of the stuff is still the same. Wire's wire, cable's cable, overcurrent devices are overcurrent. Things are getting smarter, but they're pretty much the same as it has always been when I was in the field. We just get new type of stuff emerging, and I'm always excited to look at this new stuff. And I love living vicariously through the students who send me pictures and illustrations and all kinds of stuff they run into. I love it because, again, it keeps me into it and engaged. And I love to stay engaged in the industry. I definitely do. So good luck on your exam, Miles. No, it is not an electric Jeep. I will never own an electric vehicle. Okay. Just because I'm an electrician, I will never, ever own. I wouldn't own a Tesla if Elon gave it to me, although I would take it and sell it. I'd resell it. That's for sure. I don't have a problem reselling it, taking the money. That's for sure. Hold on here. We got TJ. Morning from the other side of McKinney. What's up, TJ? You know I don't live in McKinney anymore. I moved our offices to Virginia, so I don't know what the weather's like. Give me an update. You know, I do have a house there I'm trying to sell. So if anybody you know is interested in buying a house, there's a house for sale in McKinney. It's mine. Let's see here. What are your thoughts on the National Master's License in NASCLA? I don't know. To be honest with you, I think that it's hard for all states to want to come together. They may have some agreements in some states, but then I've heard rumors that it's made it still hard for people. Even when they had that, they had to jump through hoops. So again, I'm not totally know if I mean, I like the thought of national licensing, that you can just go from state to state. I mean, electrons are electrons, right? The math is the math. I like the thought of that, but I don't know how it's been a while, been quite a few years now, and they can't really get massive traction. So I don't know. 20 degrees in McKinney. That's chilly for McKinney. Hope I left my air conditioner and my heat pump running, although it's going to probably do 1.2 million, Anthony. No, not hardly. My house in McKinney, Texas is 3,092 square feet, built in 2008, 9 or something like that, and it's selling for $449,000. I dropped it about almost $100,000. So, but it's not a fancy house, Anthony. What makes you think I'd live in a fancy house? All right, let's get back to the lesson here. Let's make sure we at least finish this today. All right, so we know what our ampacity, our secondary conductors, a minimum have to be, and we know what size they have to be to handle the calculated load. And whatever the panel is that we're installing, then we're making sure that those conductors are equal to or greater than the rating of the device that it terminates into. We got that. So the next caveat we have to meet is that those secondary conductors, they do not extend beyond the switchboard, switchgear, panel board, in our case, disconnecting means or control devices they supply. Okay, so whether I'm hitting a disconnecting means there and doing what we said earlier, or we're actually coming out of the secondary and we're going into a panel board, which is going to have a main breaker mounted on it inside of an enclosure, right? The panel board's the guts. So in that scenario, it can't extend beyond it. So what we were saying is, once those come out of the secondary, and Dan was pointing to this, once they connect into the actual disconnecting means, whatever we're doing, or the breaker in a panel board, let's say, once that takes place, then that's it. You've met that rule, right? They're not tapped onto. Again, you can't tap a secondary and come out and try to hit something else. Look, it comes straight out of the transformer right into that enclosure. That's it. So as long as it doesn't extend beyond that, then we're good to go. Next, that was probably pretty easy to do. You're just going straight from the transformer straight to the piece of equipment. In this case, our enclosure with our panel board in it, with the main breaker. All right, now, the next one is this one, secondary conductors. The secondary conductors are enclosed in a raceway. All right, so that's the first rule. So coming out of that, now what is a raceway? MC cable is not a raceway. And I think we talked about that. I think it was Manny that brought that up last time. If this is specifically saying those secondary conductors are enclosed in a raceway. So to find a raceway like RMC, IMC, things like that, EMT is a tubing, but it falls under raceway, things like that. You will find what's a raceway in the definitions of the different wiring methods that you want to use, okay? MC cable, for example, is not a raceway in that scenario. So coming out of the transformer, that type of thing, if you're going to be using this 10-foot, it's requiring it to be in a raceway. All right? Now, FMC, which we see from time to time, that's a conduit, which is a raceway. Don't confuse that with MC metal clad. Looks the same, but MC comes factory made. FMC typically is not. You would make that up on the site. Okay, now, the secondary conductors are enclosed in a raceway which shall extend from the transformer to the enclosure of the enclosed switchboard, switchgear, panel board. Again, remember, panel board is the guts inside of the enclosure, or control device, or to the back of an open switchboard. Okay? So into that. Now, what's interesting with these here it says the secondary can extend beyond the switchboard, switchgear, panel board, disconnecting means, that type of thing. It almost feels like here it says the secondary are enclosed in a raceway which shall extend from the transformer to the enclosure of the enclosed switchboard, switchgear, panel board, or control devices, or to the back of a. It seems like I would like to have said into the back of a disconnecting means as well. would have been nice because of this wording up here. But I think we're not, for all intents and purposes, we know what we're talking about. We're coming from the transformer and we're going to the equipment, and it needs to be enclosed in a raceway. Again, talk with your AHJ, have a conversation. If we want to do what Dan said, let's say, and put a disconnecting means, then I think that we just have to realize, and there's people out there that say, well, the words matter, Paul. I get it, but here it talks specifically about the secondary conductors and how they should not extend. And here it's trying to tell you how they get from point A to point B. I think you're going to actually putting in a raceway, even though you don't see the word disconnecting means here. I think you're going to be extending it in a raceway. Okay. But if you wanted to play the semantics game, the only and have some inspectors say, well, it doesn't say disconnecting means, and I'm coming out of the transformer and I'm hitting a disconnecting means, so it doesn't have to be in a raceway. I would think that he would say to you, well, look, if you're not following this entire rule, then I'm not going to let you use the 10-foot rule. And since they can only be enclosed in a raceway, the secondary conductors, then I'd rather not get in that argument with the inspector, because then he might say, well, I see what it says here, but here it doesn't say anything about that raceway going into a disconnecting means. So guess what? I'm not going to let you do it. I would be careful. This is one of those things, be careful what you ask for. The 10-foot secondary conductor rule is widely used. I mean, probably every transformer installation uses it. So I would not sow the seed of, by any inspector who could grab that and want to use that as a power grab. I'm not saying all inspectors do that. Again, don't nobody inspector get offended. I'm just saying sometimes reading the literal wordings, and sometimes may say, well, it doesn't say this, but it doesn't say that, but we know what the intent is here. Okay. So again, the intent is from that transformer to that equipment has to be in a raceway. That's what the intent is. All right. So we followed all of that. And then the last item here is very important. So once you've done everything right, you size the conductors right and everything. So this is a rule that you just have to make sure that when you're doing the installation in the field, that we have to make sure that our conductors at least meet this rule. All right. And it says, okay, for field installations where the secondary conductors leave the enclosure or vault in which the supply connection is made. So it's saying leaving the wireway, and it's leaving and it's going to your equipment. Okay. So let's say or in this case, also it's leaving the transformer enclosure and it's going to your panel. Same concept. It says the secondary conductors shall have an ampacity. Okay. So this is a minimum. It shall have an ampacity not less than the value of the primary to secondary voltage ratio. And let's say, again, in our case, it was a 480 primary and it was a 12208 secondary. So the voltage primary would be 480 divided by 208. And that would be 2.307 or 2.31. So that's your ratio. All you did was divide the primary into the secondary to get this ratio. Okay, that's what it means. Okay, so that ratio right there, multiply that by 1/10 the rating of the overcurrent device. So if it was a 200 amp overcurrent device, okay, and you divide that by 10, that is 20 amps. Okay, so in this case, those conductors have to be rated what? The primary to secondary voltage ratio multiplied by 1/10 of the overcurrent device. So there was a 200 amp overcurrent device, okay, on the primary. So I'm just throwing numbers. So it would be 2.31 times multiplied by 1/10, which is 20, and that is 46.2 amps. Okay, so those secondary conductors shall have an ampacity of not less than 46.2 amps. Probably are going to have much more than that. So this is why item number 4, for the most part, becomes a moot issue. But it's important you understand it, how to do that little math, because you never know what's going to show up on an electrical exam. And they're just trying to make sure that you know, it might say for field installations, what is the minimum size, yada, yada, yada. And so you have to, and maybe it gave you just enough information to be able to solve this. So I just want to make sure that you understand each one of the elements. But in the real world, that part's probably going to be taken care of itself. The only time that this may not is if we're dealing with a transformer that is a small transformer, okay? A 25 kW transformer or 25 kVA transformer or something smaller where the conductors may calculate out to be a certain size based on this up here. Based on this up here, okay? But ultimately, you still have to make sure that it's at least sized what? The primary to secondary voltage ratio multiplied by what? 1/10 of the rating of the overcurrent device that's actually protecting the primary. So whatever the primary protection is, you take 1/10 of that, you take the ratio, again, 2.31. We got that by taking 480, divided it into 208. And that's where we get this voltage ratio. We multiply that by 1/10 of the amp rating of the primary protection, and that determines the minimum size secondary conductors. But again, chances are it's going to be much larger than that. So usually 4 doesn't come into play. Now, let's look real quick at an example. Now, this example is available in your link, if you have link. So that's why I felt when I was thinking about this episode, I thought, this is a great way to utilize the links example and a good reason why people have link. It's also another good reason why people have our program, Mastering the NEC, if you're already licensed, because it's basically the same thing as link. In other words, you always have the code and explanation and the Fast Tracks Interact always available on your phone. And that's not for exam prep. That's the Mastering the NEC is for everybody that's not licensed that wants to stay connected with us and use us basically as their lesson tool and when you're in the field. That's what Mastering the NEC program is all about. Okay. So anyway, we want to look at this and see what the example is. So the size rated relationship between the primary overcurrent and the secondary conductors is necessary because the transformer's primary device provides short circuit ground fault protection to the transformer's secondary conductors. And that is also important to understand that when we have that item number 4, we're making sure that at least the conductors are going to be a certain size. And they may probably are going to be larger, but they're at least a certain size in order to make sure that they're going to be also adequately protected as well. Okay, so it says the ampacity of the secondary conductors must be adequate for the calculated load. Okay, so those conductors have to be sized for the calculated load, assuming you did a load calc. Hopefully you did that when you sized your transformer to make sure you know you got the right size transformer, right? At least have to do that first. Make sure you know what the loads is, right? All right, and it says the ampacity of the conductors must be adequate for the calculated load and not less than the rating of the device or overcurrent device to which the conductors terminate. Okay? Yep. So remember, Dan, that's a good point for the students. I'm talking about for use in the field. I'm talking about link. Remember I said with our Mastering the NEC, it has nothing to do with exam prep. You should never be using link with exam prep. You should always be using your code book because that's what you have to take to exam. Remember, my coffee hours are not exam prep courses. These coffee hours are not for exam prep. These are just code. So I was kind of referring to people using link when they're out in the field. They're already licensed. And that's the Mastering the NEC program is designed for people that are already licensed, not exam prep. So yeah, I would never use link for exam preparation. All right. Okay, we'll let the course do that type of scenario. All right, so anyway, so let's look at this example. All right, so what do we got here? Let's say we're going to apply the 10-foot secondary conductor protection criteria, which is 240.21C2. Okay, we're going to do this for a 75 kVA transformer, 3-phase, 480 volt primary, 28Y120 secondary. Okay, very common application. And it's using a very common transformer, 75 kVA transformer. It says the transformer primary overcurrent device is 125 amps. So it's already told us, it's already done the math, and it's telling us what the primary is. Okay, so we already know that. Okay, now what we have to determine is the minimum secondary conductor size for the installation of one of the sets of secondary conductors. Okay. All right. So solution. First thing we need to do, remember what it said? Field installation. It's got to be at least what? Okay. So first thing we want to do is find what's the 1/10 of the overcurrent protected device that's protecting the primary. Okay. Well, we said it was 125 amps. So we know that 125 amps divided by 10 is 12.5 amps. So to determine the ratio, remember what we said earlier? We take the primary and we divide it into the secondary, and that gives you 2.31. Okay, it's actually 2.307, rounds up to 2.31. All right, and so to determine the ratio, we did that in order, so it's 12.5 times 2.31 equals 29 amps. Okay, so in this case, it would be a minimum of 10 copper. Okay, if you go to table 316, and again, since we weren't given any lugs here, this is a key thing to remember. We weren't given any lug information, and you might get this on an exam, and somebody will say, I can't answer this accurately. I wasn't given enough information. Yes, you were. It never said that it was 75. It never said anything about that. In fact, THWN is only rated 75. It's not rated 90 until you put the -2 on it. So there are enough factors here for people to be able to work this out and determine what the minimum size would be. Okay. All right. So in this case, determine the minimum. All right. So determining the minimum ampacity for ungrounded transformer secondaries would be the 2.5 times 2.31, which is a ratio right here. And that would be a 10 for 29 amps. If you go to table 31016, 30 amps from the 60-degree column is a 10. Now, a 10 copper conductor is permitted to be supplied from the secondary of the transformer with primary overcurrent protection at 125 amps. The load supplied by the secondary conductor cannot exceed the conductor's allowable ampacity from 31016, coordinated with the temperature ratings of the conductor terminated in accordance with 110.14C1A. Okay? All that is extremely important. However, if that secondary conductors in this case are terminating into an overcurrent protected device, right? Then we have to make sure that they are what? We saw earlier. They have to be equal to or greater than the rating of the overcurrent device that it terminates into. Okay? So again, all those different things you have to take into consideration. And the amp rating that we got from the ratio calculations was 29 amps. So the conductor that we're using is rated for 30 amps. So that 30 amp conductor can only terminate into a piece of equipment with overcurrent device protection in it that's rated 30 amps, or to a panel that's rated 30 amps, okay? Or into a breaker in that panel that's rated 30 amps, in that example. Okay. But remember, that is an example of a minimum, because chances are that transformer, obviously it's 75 kVA, it's going to feed a panel that's much larger than that. And so those secondary conductors are going to be sized for that panel, right? So in our case, it's probably got primary, secondary protection. So that 75,000 is going to be divided by, let's just use 360. That's 208 amps. Chances are that's a 208 amp panel. Chances are they're going to be supplying it with 3/0 copper. And if that's the case, then this becomes a minimum conductor rule based on the information that we have. That's all we have. But we know that in real world, we're going to be supplying probably a 200 amp panel or even a 225 amp panel, because it's okay to do that. And at the end of the day, whatever the size of the overcurrent device that we're terminating into, those conductors have to be equal to or greater than that size. And we can't use the next size up rule, because y'all saw earlier that that's not allowed for secondary conductors. Right? So see how this all works? It's a magical dance to get used to everything. So one of the things that people get confused with is sizing the protection for the transformer, and they forget that there are conductor rules that are totally separate that you have to follow. Okay. All right. So let's take you here now. Let's go to real quick, see if we can't cover the 25-foot secondary. Now we'll talk about tap rules. All right. So this is the 25-foot feeder tap rule right here. Okay. So remember last week we talked about the 10-foot feeder tap, 10-foot tap rule. and we talked about taps in general. This week, I introduced you to secondary conductor 10-foot rule. Now we're going to be jumping back to the feeder tap rules. And now we're saying, well, can I tap a feeder and can I go up to 25 feet? Yes, under these conditions. So where are we at in the code? We're in 240.21, and we'll be looking at B21 or B2. Okay, so let's make sure we get in our code book where we need to be. Here's 240.21 right here. So here's where we're at, right here. And we're going to be looking at feeder taps again. Remember, no next size up rule. Can't do that for taps. We did the 10-foot last week. Go watch that episode if you missed it. And now we're going to taps not over 25 feet long. And again, it's very short. Okay. So what are we talking about? Let's bring you back. So here's what we're talking about right here. Okay. So we're making a tap here. Here's the feeder. Okay. And we're making a tap here. And then this, again, here it's going not more than 25 feet. Now, remember something I told you last week? A tap right here, a feeder tap, does not have to tap a conductor, folks. Okay? I don't know if I can blow this picture up a little bit. There we go. It does not have to tap a conductor in here. Okay? This could be the load side lugs of this device right here. And you can still apply the tap rules. There's a lot of people that don't understand that. If it's on the load side of that bike, there's nothing that says that it has to tap a conductor. A feeder tap has to tap a conductor. It could be the load side of the lug. So you could have, this is your breaker. This is right here, and this is a feeder. But maybe there's a set of lugs here that's being run all the way to this piece of equipment. And the 25-foot rule would apply all the way to here. So it could happen to a conductor in here, or it could happen on the load side of a breaker in here, on the load side of a main breaker, for example. Because the whole rule is this conductor is not sized based on this protection. So that's why we're utilizing the tap rules. And the tap rules simply mean that I'm tapping on something from the tap conductor does not have the same ampacity as the feeder that it's tapping onto. And the code allows this. Okay, so the maximum distance in this case is 25 feet. All right, so let's go back and let's kind of pick this picture apart. All right, so let's see here. I'm off of transformers now, but let's see here. Eric's got a question on transformer here. How many transformer can you run off a single ground rod? If I have a ground rod and it's centrally located, then I can run all, just like anything, I could run all of my panels to one rod. I don't have to have multiple rods. Now, in a transformer that's on, that's basically trying to, if we're talking, again, you got the mixes, you might have an outdoor transformer, which requires its own grounding electrode system. And then you have what may be for the building type of situation. But if they're in close proximity, if you have multiple transformers, I don't have to have separate ground rods for every transformer. If I have one that's central and it's adequately can connect to it, again, the old saying is you can't get 10 pounds of crap in a 5-pound bag. So a ground rod is a ground rod. So if you're using rods, I can run multiple transformers if it logistically works out to do so. Okay, that type of scenario. Makes sense? Let's see here real quick. Dan says, so are we switching the primer side? No, Dan. We're talking now about feeder tap rules. Okay. Last week we talked about the taps, and we talked about that time. And we have other episodes that I talk about sizing on the primary side. We have other episodes for that from Coffee Hour. We are shifting gears. These are not uniform training. Means I'm not going through every element of transformers on the coffee hour. Coffee hours are any topic that we want to talk about. So today I decided we're going to talk about, and again, if it gets confusing because we jump around, that's just the way it's going to be for people. That's how coffee hour is going to be. That means they have to watch the whole episode. You know what I'm saying? To do it. So in this case, I'm now shifting. And then last week we did talk about or a week before last, we did talk about what happens if you're supplying transformers from a feeder. We already talked about that one, for example. Okay, and that was the 25-foot feeder rule, where we're tapping a feeder and we have an overall length of 25 feet. So whether or not you had the secondary conductors were 25 feet and then the primary was the same size as the feeder, which is not considered a tap at that point, or we're tapping and we have a maximum of 25 feet to supply a transformer. That was a previous episode. Check those out. All right, so 25 foot, we're all for transformers. We're talking feeders, just a feeder, normal everyday feeder. All right, so in this case, here's the 200 amp right here, and it's tapping. It's 600 amp ahead of it, right? So this is 200 amp, 600 amp ahead of it. So we want to use these secondary. We want to use the tap rules here. Okay, so it says a 200 amp rated conductor is the minimum size allowed if the overcurrent protection of the tap conductor's line side is 600 amps. Okay, so that is 240.21b2. We'll look at it. So this conductor here looks to me, it has to be, since it's terminating into a 200 amp device, and we know we can't use the next size up rule, right? So, yep, Russ, every Monday morning, unless I can't make it, then you'll know because it'll say in the title that it's a replay. In case something comes up, I don't have internet or whatever, because I am on Starlink. So, again, I was worried whether the snow would cause that to not work, but it is. But, yes, we are live today. January 6th, for those that are watching. All right, so right here, 200 amps. But let's see what the code says about that, because, again, what do we say in our program? Anytime you see these chevrons, we want to make sure that we go look it up in the code. So we're going to look at it here. So let's look at the rules. All right, so where the length of the tap conductor does not exceed 25 feet and the tap conductors comply with all of the following. All right, first one we just saw. So this 25 foot of conductor that's tapped onto a feeder, whether it's at the lugs or it's onto a conductor, still a tap. And it says the ampacity of the tap conductor is not less than 1/3 of the rating of the overcurrent device protecting the feeder conductors. Okay, so not less than that. So let's go back to our example here. So this is 600 amps. Okay, so it can't be this feeder conductor can't be less than 1/3 of this rating. All right, so this one's easy. 600 divided by 3 is 200. So the ampacity can't be less than 200 amps. Okay. So it looks like probably a 3/0 copper, right? All right, so let's go on to the next one. Second, it says the tap conductor, number 2, caveat, it says the tap conductor terminates into a single circuit breaker or single set of fuses, okay, that limit the load to the ampacity of the tap conductor. Okay, well, that's pretty straightforward. So all this stuff is being dictated for us. Well, this is a 200 amp because of the rule, the first one we looked at. And now, since it's going into a 200 amp overcurrent device, this 200 amp device is limiting the load to 200 amps, which is the rating of the conductor. So it's all working out, okay? So, and it's terminating into a disconnect, which maybe it's a single main breaker or whatever it is. And then, of course, it's maybe feeding a panel board on the load side of this, whatever. It's feeding it. Okay, supplying it, and it's rated 200 amps. Okay, everything looks good so far. Okay, now it says this device shall be permitted to supply any number of additional overcurrent devices on its load side. So this is what a lot of people do with these tap rules. All right, so since the rule for this 25 foot that it has to terminate into a single overcurrent device or single set of fuses, but you're thinking, yeah, but I want to put more breakers in there. I want more loads to be handled by this. What's the deal? Well, it's okay as long as it terminates into that single device. It could be a panel board with multiple breakers in it, but you're hitting a main, whether it's circuit breaker or fuses. You're hitting that. Or you could be hitting a disconnect, and then out of there on the load side of this, it's hitting a panel that's maybe a main lug only panel that's got a whole bunch of breakers in it. It's a design thing. However you want to design it. The point here is that 25 foot tap conductor has to stop and terminate into either an overcurrent protected devices as a circuit breaker or fuses, either one. Now, beyond that, It can feed whatever the load calcs you've determined, how many over devices you need. You have to think about your system design. But right now, as far as the 25-foot tap rule, we done. We done when it hits that, okay? All right, last caveat right here. The tap conductors are protected from physical damage by being enclosed in an improved raceway. Okay, so here's where the inspector gets involved. An approved raceway, well, probably should say, I'd like to say listed raceway because most of all the raceways are listed. However, there are some that are not required to have a listing. Certain wireways, for example, are not required to have a listing, that type of thing. Okay, so approved raceway means that your inspector gets to look at it and make the decision, assuming it is a raceway or qualifies as a raceway, and they'll be like, yeah, I'm okay with this. This is fine. But the other thing is they can also do or by other approved means. So other approved means maybe this is where they're like, I'm okay with this in MC cable. They're fine with it, that type of thing. Again, this gives the leeway to the AHJ to be able to take your situation and apply it, okay? Now, this is a good example of showing you right here what the taps mean and in the maximum. This is kind of a neat illustration. It's very simple, a very one-liney thing, but again, it illustrates it pretty well, okay? So here it says, the following exhibit illustrates an installation that meets the feeder tap requirements of 240.21b2. The ampacity of the 3/0 AWG, the THW copper conductor is 200 amps, and it is more than 1/3 the rating of the overcurrent device, which this case was a 400 amp, okay? More than a third, because a 400 amp divided by 3 is 133, okay? So we picked a conductor that was 200 amps. So more than happy here, okay? So this is a 400, and this was a feeder, right? So this is where other people get confused. They go, that's a feeder. Wait a minute. You said that you didn't have... We weren't talking about the tap conductors now. We're talking about the feeder itself first. And yes, this is a 500 kc mil copper, which we saw is good for 380 amps, terminating on a 400 amp overcurrent device, because this is using the what? 240.4. This isn't a tap conductor. This is the feeder, right? This is where the tap rules kick in. And just in this case, it's showing them tapping onto the actual conductor. Okay, but you know what's so funny is they could actually have connected right here, and it still would have been the same rules would apply. These conductors right here would be following the not more than 25 feet tap rule. Okay, so don't get locked in your mind that it only has to tap to a conductor, because that's not the case. Okay, all right. So anyway, let's get back to the tap part. So here's the taps. And this portion right here, from here to here, okay, cannot be more than 25 feet. All right? So this is a 200 amp device. It met the rules. This conductor is rated equal to or greater than the overcurrent device that it connects into. That rule is met. It is at least a third of the rating of the protection ahead of it on the feeder. Yep. It is. It's 200 amp rated, and all we needed was 133, so we're good. But because it's a 200 amp device, because you've calculated the load, you knew what you needed to have. So that means that these conductors right here, these are the tap conductors. Remember, you can't use the next size up rule. They have to be fully sized for the device that they're terminating into, right? And that is, in a nutshell, the simplicity of a 25-foot tap rule. Pretty straightforward and gets used literally every day. I think one of the key takeaways from this for when it comes to this 25-foot tap rule is that, again, if I want to come out of that 400 amp device and take my tap conductor straight to the lugs and utilize the tap rules, then I can do that. But what people forget is that if I had to come out of, this is great. Let me bring you back to this. Let me show you. This could blow people's mind. If I wanted to come out right here, and if these conductors right here were the same size as these conductors, then guess what? This is not a tap rule. That would be just part of the feeder. In that case, you run into an issue right here. These applications means that you get screwed because you were utilizing the tap rules for a reason, right? And so now these conductors are protected at what? These conductors are protected at 400 amps. These conductors right here are no longer taps anymore. And you just happen to be feeding a 200 amp overcurrent protected device. So you're going to be limiting the load on those conductors, which are already could be rated for 380 amps. You're just, one, you got to make sure the lugs are okay. But in doing that, then you don't have a feeder tap. You don't have feeder rules because everything is the same size. The whole point of a feeder tap is to be able to have a conductor that is smaller, less amps than the actual point of connection to the tap or the feeder or at the load side of the breaker. You get my point? That's the whole concept of the feeder tap rules, all right? And so we'll get into next week, we'll look at not next week, tomorrow, we will look at the 25-foot secondary conductor rules, and then we'll come back and we'll take another quick peek at the feeder one where it talks about 25-foot for the primary plus the secondary. We'll recover that again just by itself because that's a fairly big one. And that is where you tap a feeder in order to be able to supply a transformer. Okay, and I'll give you some scenarios in that one where you say, well, that 25-foot primary and secondary, what if the primary conductors are full-sized? The same, they're not reduced. Then that extends your secondary conductors. Again, that's quite interesting in that primary, secondary feeder tap rule. Okay, that type of thing. Pretty interesting. And so we'll cover that on the very next episode. So you see how we're kind of piecing these things together. All right. So before I leave this episode, this is a lot of info. People say, Paul, you're going too quickly. Paul, I don't get it. This may not be the training for you. This may not be right for some of you out there. And again, I'm not trying to appeal to everybody. Okay. People think that I should be making content to appeal. That's not how I make content. I don't care whether people watch my content or not. I am financially secure. I don't make money off of my videos. Okay. My courses are where we do things. So when I'm teaching something, I'm pretty much not following any rhyme or reason unless you request something. And if you request something, I typically will go into that type of scenario. Okay. But yeah. So yeah. One of the things Eric points out, yes, all that scenario is you also better make sure your lugs can handle everything. Okay. So just because we go bigger on things and go larger on the conductors, always at the end of the day, what could screw you could be the rating of the lugs that screw you. Okay, maybe, and anybody out there that ever says you remove a strand in order to make it fit into a lug, you need to leave the trade. You need to become a plumber or something like that. Okay, I'm just saying. Okay, no offense to plumbers. I'm just saying. All right. Thank you, Dan. I much appreciate it. All right, everybody. I went a little over, tried to get as much as I can in these coffee hours. I encourage you to go back and watch previous episodes. They're all available on our YouTube channel, and there will also be a special channel for coffee hour over on Fast Tracks Tube coming in the next day, if I can get to it. Love to have you go over there and watch episodes. If you're a subscriber, you'll get them all access to them. If you're not a subscriber, you won't get access to them in that unique player because it's only for the subscription platform. And then slowly, everything that you might see on YouTube will slowly leave YouTube because I'm only leaving these episodes up for a certain length of time before we move them. Okay. Again, I am not about teaching the masses. If you can't join me live, then I don't really want it to sit forever on YouTube because I'm not here to train the next generation. These are for you folks live. And then I move it to our platform. Okay. Does that make sense? Hopefully it makes sense. All right. Anyway, thank you guys. Appreciate you. Thanks for joining me. Get a good start to your week. Make sure you got enough coffee in you. Oh, by the way, these are one of our mugs. This is the Trademan series. We have them in Journeyman and Master. We have them in white and black available on our website. And they're all available. And by the way, shameless plug, we have our coins, a bunch of different coins in the engraved products. This is a Journeyman one, but we have Master or whatever. So please go check them out. And Russ, go wake up Peggy. Get your day started out there in Arizona. All right, folks. Till next time, stay safe. God bless. We'll catch you on the next coffee hour.